Today, it's my great pleasure to introduce Professor Chen. I mean, it's always a pleasure to have a Wolverine to be introduced. So apparently, Professor Chen got his PhD here at the University of Michigan some time ago. And then he launched a fantastic career where he stayed in the US for a while, and then he has been in the City University of Hong Kong for a while. The number of awards and guest professorships he had is almost impossible to list. But also, you can take a look at the flyers, and you will see that he is a member of many prestigious associations, often in the level of fellow, and he has done very substantial work in the area of time delay systems in the last couple of decades. And without any further ado, I would like to introduce Professor Jie Chen. So Jie, please take it away.
Okay. Thank you very much, Gabor, for the very kind and humble introduction. It's a privilege to be invited to this forum. And for that, I'd like to thank Win and Gabor. I believe Win will join shortly. And the TDS working group in general. And to the friends and the colleagues here, thank you for your participation. It's great to see everyone. So what I'll talk about today are some of my works and thoughts on time delay systems, in particular linear delay systems. And some of these results, I'd say, are rather old by now, but some others, hopefully, are still quite recent. So in retrospect, I guess I'm not a hardcore person in time delay per se, although Gabor put in many nice words. Also, probably some of you know that I wrote a couple of books on the subject. For that matter, what I talk about may not be a mainstream time delay theory, but probably more a somewhat unorthodox viewpoint. So this explains a bit the subtitle. But why did I care about time delay in the first place? As I, did work on a few other things. I'd like to think it's because of its intrinsic interest and because of its practical relevance. A simple answer is that time delay is everywhere, ever and omnipresent. So from, as you can see, classical mechanical systems such as a gyroscope, a milling cutting process, and to classical economical models, and further on to today's communication networks, biological systems, and to multi-agent networks and cyber-physical systems. So you see all these kind of examples that we encounter very frequently in the literature. But what I really want to touch upon is a much older, a truly immortal example, the Dujiangyan irrigation system. I myself made several trips to this site, and every time I was very much inspired, marveling at its grandeur and ingenuity. I would argue, and I hope you will agree after my explanation, this is a delay system. So just very briefly, the Dujiangyan project was constructed in 251 BC. That is more than 2,000 years ago, led by its chief architect named Li Bin. Here you see the aerial view of the project and the statue of Li Bin, which is also like 2,000 years old. It's a colossal, highly sophisticated system consisting of multiple cascades extending several miles long along the Min River in southwestern China, near Chengdu, the place where you probably have heard of. That's the place you see pandas. The main purpose for the project was, and it remains to be, because it still functions very well, to divert the floods in the flooding season from the downstream Chengdu Basin, the city vicinity, that is, while in dry season to provide sufficient water supply to the city and its vicinity, where there's a large expanse of rich farmland. And these bluish lines that we see today on Google Maps are the outcome of this project. They're all tributaries coming out of the Dujiangyan project, which is at the top left corner, while down to the bottom right, it's the city of Chengdu. You see those rivers surrounding the city center. Okay. So for that to happen, they built really a dam or a levee in the center of the river. So let me pick up the laser point. So this is the this is built in the center of the river. Okay, and while cutting also open a water channel on the right from the mountainside. Yeah. So this was done by fire and power because it was before the invention of gunpowder. Okay, so the river is divided into two parts. The outer river on the left, and that would go around the city, and the inner river to the right, which flows into the city. So perhaps this schematic diagram illustrates things better. The system consists of three essential parts. The fish mouth, where you see this, the blue arrow points to, divides the river into the water flow into the upper outer river and the lower inner river. And according to some seasonally changing proportion, for example, like in the flooding season, 60% of the water will go to the outer river and 40% will go into the inner river, and this would reverse in the dry season, okay? So since the inner river is much deeper and because of its curvature carved deliberately, it flows much slower than the outer river. Now, when observed at this mouth of Treasure Bottle, where the inner and the outer river connects via a back channel, that is where this red arrow points to, and there's a differential between the two currents. So when the inner river reaches to this point, there's a de facto delay. Now, because of the delay, it creates negative effect, something we know quite well. Delay oftentimes leads to things that we don't like. And in this case, is the accumulation of the silt and the sediments in the inner river, sands and the stones. So this is bad. The problem is solved, however, when the floods come, when the water, this mouth of Treasure Bottle blocks the water, right? So when the water at the Treasure Bottle reaches to a level higher than this internal levee, you see the green arrow points to, this is called the flying sand levee, just acting like a valve, an actuator. The excess swirling water, and these are all sort of because of the curvature, so you get this swirling water would overflow to the outer river and takes with the sand and the stones. Okay, so you see that. So behind this project, you see the negative effect of time delay. You also see some control actions that would correct this undesirable effect. It's truly an ingenious design. So we see that delay arises for a wide variety of reasons. We study them because they may be physically significant and hence cannot be neglected. or we want to include the delay in our system model when a higher performance goal calls for it. Or they can simply be taken as approximations of infinite dimensional dynamics, as we know well. It goes without saying that time delay systems have been long and well studied, certainly. The earliest work can be traced back to Euler in the 18th century, as it is so argued. And we indeed have come a long way from differential equations to quasi-polynomials and then to functional differential equations. There has been particular explosion of ideas and techniques, I'd say, in the last 3 decades or so, due to the invention of robust control and LMI. And more recently, we have other things like trajectory-based methods and so on. So undoubtedly, we control people have quite a lot of credit to claim in its evolution and development. We should be quite proud. And what stands out in the classical analysis, in my opinion, is this so-called two-variable criterion, really an umbrella for many of its variants and other things. It was very popular in the 70s and early 80s. So to make a long story short, basically in this method, you need to solve simultaneously 2 algebraic equations of 2 bivariate polynomials, well, which in one way or another requires illuminating one variable. The advantage of the 2 variable criteria is quite clear. It provides a necessary and sufficient condition to exact solution. The downside, however, is that the variable elimination is very difficult to implement numerically. It virtually requires a symbolic computation. And this is perhaps why, and this is my take, it's mainly effective for low-order systems with few delays, essentially limited to second-order systems. On the other hand, what has been dominating the scene for quite some time is, as we know it, LMI tests. The sheer volume of the published work on this approach is truly overwhelming, and if I may, even a bit scary and bizarre, just way too much, I felt. The LMI tests are readily or not so readily computable, depending on who you talk to and depending on your perspectives. They also tend to be conservative. So in summary, I want to be a bit bolder here. Over the years, these 2 methods have emerged as perhaps the most popular methods, though there are other methods I just mentioned. They are the cream of crop. And somewhere in between, we explore a third alternative. This is an operator-theoretic, non-LMI approach. The whole thing, and this is what I'm going to talk about for much of my talk, boils down to solving 2 problems in sequence. A pure mathematical problem concerning the perturbation analysis of matrix value functions, okay, in the first place. And next, a control problem, that is the stability problem. But the thinking and the idea actually goes further beyond to stabilization and robust stabilization of delay systems and to a bunch of other problems as well. This is what I meant by third eye approach. We look at the things somewhat in a different way. But we need to be very careful with the third eye. So you have seen this word a few times, though it is not at all unfamiliar, especially in Oriental philosophies. For example, in Hinduism, they have a god Shiva. God Shiva's third eye symbolizes his wisdom, and well, that's a good thing. For those of you who have followed Game of Thrones, a blockbuster TV series that went crazy a few years back, you can't miss the three-eyed raven, yeah? for good or for bad, which has the capability to see into the future. Now, in the Chinese Taoism, we also have a three-eyed god, the fierce warrior Erlang. But the legend has it that his third eye often sees things wrong. So maybe I should add a footnote here. Beware, you want to be very careful with what I said, because my third eye may see things wrong. So now coming down to real business, I shall consider for matters of simplicity the so-called commensurate delays and retarded systems. So linear delay systems of this kind can be modeled by a state space equation or equivalently a quasi-polynomial. So for our colleagues here, everything should be rather familiar in this setting. The system as we know it is stable if and only if the characteristic function of this system or characteristic quasi-polynomial has no root in or zero in the closed right-hand plane. Notice, however, this is a transcendental function, and so it's not easy to check the stability even with a fixed delay, less that the delay may vary. Okay. But still, we could ask ourselves a number of fundamental questions. For example, suppose that the system is stable with no delay. Yeah? Then what is the largest delay variation it can tolerate before losing stability? I call this problem the delay stability margin problem, which is a particular kind of robust stability problems. More generally, we may wish to know more. For example, for what ranges of a delay the system is stable or unstable. That is, we like to get a full picture of stability and instability. And furthermore, from a control perspective, we want to know in what range of delay a system can be stabilized. In other words, there's a certain feedback controller that can stabilize the entire family of the delay plans within that range. This clearly is a robust stabilization problem. I'm not completely sure, though. I will have time to get to this part, but I'll try to give a shot. What happens is that the delay margin and the delay interval problem are rich enough to take us quite some time. So for now, let us focus on the stability problem. In a nutshell, the essential idea in this approach, the third alternative, is to conduct a two-step procedure. And the idea goes as follows. In the first step, we want to ascertain, we want to find out whether the system has imaginary zeros, okay? If it doesn't, it's either stable or unstable, shared by continuity, end of story. So this is, the problem becomes trivial. Now, if it does, we go on to the next step to determine whether the imaginary zero would cross the imaginary axis, okay? And if it does, in what direction? If some zero goes from left to right, crossing the imaginary axis, the system is stable. Conversely, if all the imaginary zeros traverse from right to left, then the system becomes stable. So as simple as that. Now, this latter problem, the crossing of the imaginary axis, is colloquially known as the stability switch problem. And I hope this animation of system eigenvalues can serve to illustrate the stability switch problem better. Here we have a system depending on the values of the system parameter alpha. an eigenvalue may cross the imaginary axis. For example, the red curve touches on the imaginary axis and then bounces back. The green curve or never touch it. The very behavior of the imaginary eigenvalue, hence, is very important. It works like a switch to stability or to instability. Hence, called the stability switch. Now, this problem has been open for quite some time in the time delay community and by applied mathematicians alike, at least like open for 30 years or so. The essence lies in how to exploit the asymptotic properties of the eigenvalues on the imaginary axis. And ultimately, the answer to this problem will enable us to determine the ranges for stability and instability. And the enabling tool for that is Cato's operator perturbation theory. So we come down to the first problem. So what is operator perturbation all about then? Well, it was initiated by Erwin Schrödinger in his study of quantum mechanics, although slightly earlier, Lord Rayleigh touched upon the idea in his study of acoustics and mechanics. Okay, so the idea, the problem were later further developed by a Göttingen mathematical physicist named Franz Relic. Okay, he was once the department head of mathematics. Actually, was the boss to Hilbert. And finally became a mature branch of mathematics through the minds of Berkeley mathematician Toshio Kato, who wrote his masterpiece, Perturbation Theory for Linear Operators. Along the way, we also made some further developments, which I tend to believe is non-trivial for its own sake as a mathematical result, and perhaps its meaning as a mathematical result would be more important, or at least equally important as the analysis of the stability of delay systems. And certainly, it's quite tangible to solving our problems in this context. So to pay my respect to these grandmasters, I put up a tiny photo of my own down at the corner, hidden somewhere, also in black and white, just to be aligned with them. And clearly you can see that it belongs to a past age, both in terms of the black and white photo and in terms of the age. You don't see the G today as the one in this photo. So specifically, the theory concerns a linear operator, or make it simpler, a matrix value function Tx of a real variable x. This is very important, okay? Matrix valued and one real variable. And actually, this Tx has to be continuously differentiable with respect to x, okay? So assume that Tx is analytic at the origin, namely, it can be expanded in terms of a power series. Then Cato says that the eigenvalues of Tx as a function of x, clearly, can be expanded in a power series or a Taylor series, same thing, or a so-called Puiseux series, depending on the multiplicity of the eigenvalue, okay? So a Puiseux series is not something we see oftentimes. It's a series in terms of fractional orders. In particular, Cato showed that when you have a so-called semi-simple eigenvalue, then you can expand the eigenvalue also in a power series. Namely, the eigenvalue is also analytic, whose first order coefficient can be computed from a projection matrix P given at the bottom page, at the bottom of this page here. So here by a semi-simple eigenvalue, we mean the underlying matrix when you do eigen decomposition can be fully diagonalized. Okay, so it's a very special case. It would be clearly of interest to determine also the higher order coefficients. So again, in the case of a semi-simple eigenvalue, Cato came up with a iterative reduction procedure. And basically, you construct a reduce operator, okay, reduce in the sense that the order in X, okay, is reduced by one. For example, this tilde t operator, okay, the order is reduced by one because well, when you calculate this resultant, you divide it by X, so the order will be reduced by one. So what you can do there is you get a first order expansion for this tilde t, right? And that gives you iteratively a second order series for the original tx, right? This mu sub ix is the eigenvalue of the tx, right? So if you get the first order expansion for t tilde, you get the second order for the original tx. So in principle, you can keep iterating this procedure to any order you like. Of course, it gets progressively more complicated. So much so, we do have a way to handle semi-simple eigenvalues. Cato solved the semi-simple case completely. The case of multiple non-semi-simple eigenvalues is fundamentally different and more difficult. And this is also where Cato's theory falls short. Okay, but it's something that we cannot get around or get away or bypass because we do encounter multiple eigenvalues in stability analysis. So what we mean by non-semi-simple eigenvalue is an eigenvalue that cannot be diagonalized. That is, when you do an eigen decomposition, okay, you will get a Jordan form instead of a pure diagonal matrix. Namely, we have a true repeated eigenvalue, okay? So why is this case difficult? It would suffice to hammer home the point using this almost trivial example. So what we are seeing here is an operator whose zeroth order matrix T0, which is this constant matrix, has a non-semi-simple eigenvalue at the origin, okay? With multiplicity 2. The matrix T0, that is this matrix, is already in Jordan form, okay? Now, if you calculate the eigenvalues of Tx directly, which you can do because this is a 2 by 2 matrix, right? It's trivial. This is the answer you have. You get this eigenvalue as plus minus x raised to 1/2. Now there's an issue here. In this case, there's a singularity at the origin. Why? Because the eigenvalues splits to a multi-value function, and therefore it's no longer analytic, okay? Now, since it's non-analytic, there's no way for it to be expanded in terms of Taylor series, a well-known fact we learned from the first year calculus. Instead, it is in the form of a Puzo series with a fractional order of 1/2. So you have two eigenvalues, plus x raised to 1/2 and minus x raised to 1/2. Okay, so this is the expansion formula in terms of a Puzo series. So as you may imagine, in general, non-semi-simple eigenvalues present a very difficult problem. There are a lot of complications. Our main effort in this work though motivated by time delay problems, in fact, has been largely devoted to solving this mathematical problems, which fortunately has led to a similar reduction procedure. And here it is. It's a more sophisticated, doubly iterative procedure. Recall that in the case of a semi-simple eigenvalue, Cato had just one iterative equation. And in this case, we have a doubly iterative procedure. Being doubly iterated, by doubly iterative, I mean there's also iteration formula for this operator T sub kx, which is kind of looks complicated, so I didn't put up here, okay? So the results shows that now the eigenvalue can be expanded via a double iteration of continuous m's roots of unity, okay? Leading naturally to a Puiseux series with a fraction order 1 over n. So by now, pretty much we have the necessary means to deal with both semi-simple and the non-semi-simple eigenvalues. So we have a complete answer. But we still need to address computational issues, that is how the coefficients may be efficiently computed. So we went one step further, and this is also mathematicians like Cato would not bother with. But we have to face it. And this result shows how the first order coefficients, whether you have a semi-simple eigenvalue or non-semi-simple eigenvalue, can be computed. For a semi-simple eigenvalue, you simply compute the eigenvalues of a matrix as given here, and I explain what this stands for. And while for the non-semi-simple case, you calculate a scalar constant, okay? And so in both cases, you see that you need the first order derivative very naturally of the operator of the matrix function, t prime 0, okay? And the matrices and the vectors required in the computation that we saw on the last slide are found directly by conducting eigen decomposition. So you have the eigenvalues, so you do a eigen decomposition of this matrix, T0, where the matrix Q consists of right eigenvectors and R consists of the left eigenvectors. And in the case of non-semi-simple eigenvalues, some of them will be generalized eigenvectors, okay? So you see that here we have the cases of semi-simple eigenvalue. So you have a fully diagonal matrix once you do this eigen decomposition. And here you have the non-semi-simple eigenvalue where you get the Jordan form, yeah? So this is all you need to do with first order coefficients, one eigen decomposition, okay? And the second order expansion takes another eigen decomposition. So in the semi-simple case, it suffices to compute the eigenvalues of a similar matrix, which now understandably involves the second order derivatives of the matrix value function t double prime 0, okay? So all in all, it remains computationally simple and easy, at least systematic. The non-semi-simple case is more delicate. We now need to address multiple different scenarios because the Jordan form, if you recall, in general can be further decomposed into smaller block diagonal Jordan blocks, okay? So you have that kind of smaller cycles, yeah? What you can do is to calculate a sequence of index numbers as given here, which I call non-semi-simplicity index, all right? And then you decide accordingly. For example, if this lambda 1 is not equal to 0, it's non-zero, you have 1 full Jordan block and get a Puiseux series with a fraction order 1 over n. Now, if lambda 1 is equal to 0, but lambda 2 is not equal to 0, and bear in mind this can happen, then you actually have two Jordan blocks, okay? One is just the eigenvalue itself. The other is a m minus 1's order. So you actually get two branches, two different expansions. So with one, a Puiseux series with the order 1 over n minus 1, and the other is actually just 1. That's actually just a normal Taylor series. So on and so forth. So you can sort of deal with all these cases. So with the perturbation results in mind, let us now return to the stability problem to see how it can be analyzed as an eigenvalue perturbation problem. So I probably need to pick up the speed a bit. Recall that in the first step, we want to, this is a two-step procedure, which I mentioned at the outset. So in the first step, we want to determine the critical imaginary eigenvalues and critical delay values, okay, if any. How do we do that? Well, we still start with the two-variable criterion. Make no mistake, this is the foundation, the root of the problem. It's both necessary and sufficient, right? Instead of seeking to solve the bivariate polynomial directly, however, we do something different. We know it's very difficult to solve the simultaneous two bivariate polynomials because basically you cannot do without doing symbolic computation. So an analogy can be made here. When you have a polynomial of one single variable or equivalent a system without delay, you're asked to check stability. What do you do? Well, there are two ways you can do it, right? You can compute the zeros directly, or you can use Ross-Hewitt criterion. And the latter, as we know, is more desirable, okay? So what we are trying to do here is something similar. We use this Chen criterion to determine the root distribution of a bivariate polynomial without actually solving the polynomial equations, without actually solving the zeros roots, so as to bypass the difficult step of variable elimination, okay? So to do that, we treat the bivariate polynomial as a complex polynomial of one variable, say in Z, okay, with varying coefficients. Now, since we care about imaginary zeros only, it suffices to restrict to the imaginary zero axis, okay? So now you have the problem if the polynomial effective reduced to a polynomial of a real variable omega that's considered to be every time you fix this omega, then it's a complex polynomial of in Z, okay? So we then apply the Chen-Cohen criterion to this polynomial in Z, and that results in a matrix polynomial equation in one variable, okay, in omega. And then the real solutions give us the imaginary eigenvalues, J omega. And in turn, we use it to solve the critical delays. So all in all, we solve a matrix pencil or a generalized eigenvalue problem, and that gives us all the critical delays and critical imaginary eigenvalues. So this completes the first step. We determine the critical values of the delay, okay? And in the next step, we remove the stability switch problem as one of eigenvalue perturbation, and this is simple. Specifically, at each critical delay, let's say call it tau star, we construct a linear operator so that it has the corresponding imaginary eigenvalue at the tau star. And this operator is clearly analytic and can be expanded in a power series. And the coefficient matrices can be easily determined. For example, here, recall previously we have t prime 0, right? The first order derivative of the operator. So it shows the first order coefficient matrix. So by application of the perturbation results, we can write down immediately the eigenvalue series and check those conditions, see whether the critical imaginary eigenvalue would cross the axis. So again, all it takes is one eigen decomposition for the first order condition, okay? I want to emphasize specifically that this eigen decomposition and the imaginary eigenvalue can be computed all at the same time in a single shot. And this is the beauty of it. And so it does not require any additional computation. Why? The matter of fact is that in the first step, when you compute the imaginary eigenvalue, you are already doing the eigen decomposition. It comes free, the second step here. And this seems coincidental, but a bit magical. We use the eigenvalues to determine the critical values, critical eigenvalues and critical delays, yeah? And we use the eigenvectors. Recall that when you expand this series, you use the eigenvectors. We use the eigenvectors to check the crossings. They just come together perfectly. So there's no computational overhead being wasted here. So in the case of a semi-simple imaginary eigenvalue, we may then check. So this is here you have this first order up to second order expansion of this imaginary eigenvalue. All right. So we may check to utilize the first order condition, we may simply just check the real part of the first order coefficient, this lambda 1, which in general can be a complex number. So we check its real part. If it's greater than 0, yeah, the eigenvalue goes from left to right, okay? If it's negative, it goes from right to left. And it could be the case, though, that the real part is equal to 0. So in this case, this first order test would fail, okay? Then under that circumstance, you go ahead to check this second order coefficient against the real part, okay? So this is how it works. And it becomes especially simple when the eigenvalue is distinct, okay? So you simply check the real part of complex scalar. So when you calculate the eigenvalue, you have the right eigenvector R1 and left eigenvector Q1. So you just check this complex scalar. And likewise, we have the first order condition and the second order condition, okay? And both are simple enough. Now, what about non-semi-simple eigenvalues? The situation becomes a bit murkier. As you may recall, there are a lot of different scenarios here. But generically, since we are to compute the mth roots of unity, yeah, the eigenvalue will now split into several branches, with some going into the right half plane and the rest going to the left half plane in equal angular distance. Because the scenario you see is that we'd have this be eigenvalue behave like e to negative j theta, and theta are a bunch of angles in equal angular distance. So in this case, the system is generically unstable. Okay. And let me now use a couple of examples to illustrate the results. Here you see a fourth order system with 3 commensurate delays. On the surface, it doesn't look that complicated with all these zeros and rounded up numbers, but that's a deception. If you are after a necessary and sufficient stability condition, it is not that simple, in fact. It might be nearly impossible using any other method to get an exact condition, okay? So with, and also bear in mind that you want to use directly the 2-variable criterion, and this is a first order bivariate polynomial. We know quite well in general, if you cannot express analytically the solutions of the roots of a fourth order polynomial, okay? But with the eigenvalue perturbation analysis, it seems both efficient and easy. For example, you just go through step 1, okay, and then you do the eigen decomposition and found the imaginary eigenvalue, this J 1.3026 at a critical delay value 0.3786, okay? You do eigen decomposition, you can find the corresponding eigenvectors, right and the left. And this is a simple, distinct eigenvalue, so you just need to compute this coefficient. Its real part is positive, then you know this, you claim that this as tau varies, this eigenvalue would go into the right half plane. The system is unstable, okay? Well, and this animation done exhaustive computation confirms that this is indeed the case. This is represented by this red curve. The eigenvalue crosses the imaginary axis into the right half plane. As another example, we analyze the stability of this second order system. Well, here for second order system, you can actually calculate by hand. That's AKA symbolic computation. Though you cannot do it with the previous first order system. What is particularly interesting here is that it's this green curve that you just see immediately, which corresponds to alpha, this parameter in the system equal to 1. It turns out in this case, the first order condition is inconclusive. The real part is exactly equal to 0. So we have to resort to second order analysis, and the real part of the second order coefficients tells us that it's negative. So that means this eigenvalue would go into the left half plane. So it bounces back. The theory tells that, exactly that. And in the third example, we have a non-semi-simple imaginary eigenvalue with multiplicity 2. The theory again predicts exactly the asymptotic behavior that the eigenvalues will split into 2 branches with the departing angles, pi/4 and 5 times pi/4, and the simulation coincides again with the prediction. So what is good of all this anyway? I'd say it's computation, it's purely computation, okay? Compared to the conventional 2-variable criterion and similar results or its offsprings, we do numerical instead of symbolic computation. That is fundamentally more efficient. You can really solve high-dimensional problems. In comparison to LMI test, the main advantage here is that we have a necessary and sufficient condition. As a matter of fact, and this comes to be good. Computationally, it also feels better. We don't need to solve any optimization problem, but instead a standard linear algebra problem. And the complexity, as we see from the button here, is much lower, okay? So I think I still got, what, 5 or 10 minutes to go, Gabber. Hello?
Yeah, maybe about 5 to 10 minutes. Yeah, sure.
Okay. Yeah, 5 to 10 minutes would be great. I recall that we sort of like started 5 minutes late, right? So
Yeah,
that
we
would
had a little
allow me,
delay.
yeah. That would allow me to just finish this part of stabilization. So so let me now switch gear a bit to touch upon the stabilization problem. Recall that we want to determine the largest range of delay so that the system can be robustly stabilized by some LTI controller within that entire range, okay? So mathematically, this amounts to finding the delay stabilization margin as defined here. Basically, you want to find the largest range of delay so that there's a certain LTI controller stabilizing this delay plan. Okay, so very simple definition. The problem is rather reminiscent of the well-established gain and phase margin optimization problem. Two of the classical solved H-infinity control problems are solved in the, actually the gain margin optimization was solved in late 70s, I believe 79 by Alan Tannenbaum, and phase margin was solved a couple of years later, also by him. He published those results in a somewhat obscure journal. Yeah. So the difference between the delay stabilization and the gain margin phase margin optimization lies in the multiplier. Okay, the multiplier to the rational plant, be a exponential function e to negative tau s, or a real scalar k, or complex scalar e to negative j theta. Unfortunately, this difference is by no means simple. The problem is much more challenging and has been open ever since. This is still, up to this day, still an unresolved problem in general, okay? The trouble, as you can understand easily, is we now have an infinite dimensional problem. So taking this difficulty into account, we say, okay, let's settle for less. Say we'll be happy with a lower bound or a sufficient condition if we cannot get a necessary sufficient condition. So it turns out with this compromise, it can be accomplished by solving another H-infinity optimization problem approximately, say by using rational approximations. And this actually comes down again to a two-step procedure. First, you can formulate a lower bound, this tau submean, in terms of H-infinity problem, which, however, involves an infinite dimensional weighting, okay? This problem is still difficult to solve. And in general, even you can solve it, it leads to an infinite dimensional controller, okay? So that's not desirable. So we say, why don't we try to approximate this infinite dimensional weighting using a finite dimensional weighting, a rational function, that is. And then the problem can be reduced to a finite dimensional H-infinity optimal control problem, which can be solved using a variety of techniques, such as Nevalin cake interpolation. And this idea works. But for that purpose, and this is crucial, we need to carefully construct a delay-dependent rational function, which, in addition to satisfying some other properties, would overbound, as you can see, would overbound this weighting, the infinite dimensional weighting function, okay? And bear in mind, the usual party approximation will not work because in the tail of party approximation in frequency, it would oscillate, okay? So it would not totally bound this function. But there are quite a few such functions, from the very simple, such as a pure differentiator, to the more sophisticated ones. And the best we came up with, this is all due to the hard work of my students. We came up with this fifth order function given at the bottom of this page. I think it's kind of a blur here. It overbounds this function e to negative j omega tau minus 1 very closely, okay? So with the rational approximation, we then solve a finite dimensional H infinity control problem, and correspondingly, we get a lower bound, this tau underline, okay? And what you need to do is to compute the largest positive eigenvalue of this constant matrix. And this is a general result. It can be applied to plants with arbitrary many unstable poles, nominal phase zeros, namely the most general scenario, okay? What is perhaps more gratifying, at least this is really a good news to me, is that it also provides a tool that would enable us, that would give us the kind of insights we desire. For example, we can get analytical results. Here, just two simple cases. We have a whole series of such results showing how the lower bounds on this delay stabilization margin would depend on the, would be affected by the nominal phase zeros and unstable poles. It shed a lot of light in terms of the difficulty of controlling a delay plan, okay? I should also add that we can and have actually extended these results to a couple of different settings. MIMO systems, systems with time-varying delays, systems controlled by PID controllers, and further to network control and multi-agent systems. So you may be a bit, you may wonder why it can be applied to systems with time-varying delays, because all we apply here is LTI techniques. Simple, you try to overbound that time-varying delays using the LTI ones. All right, so I guess it's about the time. So let me now, I'm watching on my cell phone, okay? Let me wrap up my talk. What I have presented in this talk is a operator-based approach for stability and stabilization problems of time delay systems. For the stability problem, the key is to determine the asymptotic behavior of critical imaginary eigenvalues. And this, I hope that is clear from my presentation. And this can be done by solving a generalized eigenvalue problem. And so, in general, it's both efficient and accurate. You solve a linear algebra problem. The beauty of the result lies in that not only do we use eigenvalues as we always do, all right, okay, we also exploit eigenvectors so as to utilize to the maximum the computation to the fullest. We didn't waste any computation, okay? As another point, while continuity of eigenvalues has played a central role in stability analysis in the study of delay systems, in the study of robust stability and robust control, okay? The continuity plays a pivotal role, okay? But I felt that through this work, the analyticity of eigenvalues might play an equally important role and should not be overlooked. And this work gives one such example. So as far as the extensions are concerned, there are quite a few, but I shall not burden you with any additional technical problems. So let me just conclude my talk by acknowledging students and the friends, especially those who work with me on this scene. So you see, Silvia Niculescu, and I collaborated a lot with him on these problems. Vladimir Haritonov and Chen Ku, we didn't really work together. We didn't co-author any single paper, but somehow, strangely, we wrote a book together. And also my students, I learned a lot from all these students and the colleagues. So they are truly my third eye, okay? To cap it all, here it goes with a verse on delay or time lag, the wordings we use by contemporary English poets, Elizabeth Jennings, okay? So time delay indeed dazzles and teases, just like, Van Gogh's stars, mysterious stars, invites us to wonder. So Gabor, I guess that's all. Thank you all very much.
Well, thank you very much, G, for such a nice and informative talk.